Good day everyone, I am Maria Ricajoy Ambasadre from the Group 8 and we are going to present the simulation of shop model uneven desk using the application of the SolidWorks. So our model name is shop model uneven desk and has a current configuration of default. Let's talk in its study properties. So the study name is frequency 2 and has a analysis type of frequency, and the mesh type is solid mesh, and the number of frequency is 5, and the solver type used is direct sparse solver. When we say direct sparse solver, it solves the set of equations directly without any approximation and no error associated with the setup solution process. So it is nice to use this kind of solver when you are going to make this kind of model. And the soft spring is off and it has a automatic and compatible bonding option, and include the thermal loads in the thermal option, and has a 298 Kelvin zero strain temperature. So in the units, it used the SI units, and when in length and displacement, millimeter, in temperature, Kelvin, in velocity is rad per second, and in stress is Newton per meter square. So let's talk about its material properties. So in a properties, it has a plain carbon steel, and the model type is linear elastic isotropic. When we say linear elastic isotropic, a material is used to be isotropic if its properties do not vary with direction. Isotropic materials therefore have a identical elastic modulus, a Poisson's ratio, coefficient of thermal expansion, thermal conductivity in all directions. So the term isothermal is sometimes used to denote materials with no preferred directions for coefficients of thermal expansion. So in our model, the material properties has a yield strength of 2.20594 times 10 to the power of 0.8 Newton per meter squared, and has a tensile strength of 3.99826 times 10 to the power of 0.8 Newton per meter squared, and has a mass density of 7,800 kilogram per meter cube, and has a elastic modulus of 2.1 times 10 to the power of 11 Newton per meter squared, and has a Poisson's ratio of 0.28, and the thermal expansion coefficient is 1.3 times 10 to the power of negative 5 Kelvin. So let's talk about its loads and fixtures. So in centrifugal 1, the angular velocity is 120 rad per second, and the angular acceleration is 60 rad per second squared, and when in gravity 1, the values is 0 to negative 9.81, and the units is meter per second squared.
SolidWorks has made working with connectors quick and easy, replacing the geometry of the real hardware with idealized virtual connectors. These simulated connectors impose the behavior of their real counterparts on the rest of the design without requiring the painstaking analysis of each pin or bolt. Simulation takes no shortcuts in accuracy with its virtual connectors, but by putting many of the tasks formerly performed by analysis into the software, it speeds up the simulation process, leaving you more time to do what you do best in designing. So this part shows what type of support or fixture used for the simulation of shop model and even this, and that is bearing support. A bearing connector is a combination of spring elements that joins two concentric cylindrical parts and mimics the behavior of a real-life bearing, allowing for translation and or rotation between the two parts. Bearings are essential components of many designs because They allow smooth motion while reducing the friction as compared with other connectors. SolidWorks provides you with virtual bearing connectors that replace manually generated models of these parts but create the same effects on the rest of the system. Next is the mesh information. So the type of mesh is solid mesh, and the measure used is standard mesh. As you can see, the image shows the model which has a shaft and the uneven disc, or R damper of the model. For this part, it shows the details of the sensor, and the sensor name is frequency, since that is what we want to detect. So the frequency that is detected in mode 1 is 18 Hz.
So, in this slide, nakita na to nga natay model nga shaft with uneven dimension and surface area. So, this is the resultant amplitude plot for mode shape 1. So, natay red part and blue part sa shaft, and the red part is kanang nasa disc and ang blue part is the rad. So, the red part is the maximum nga murag affected siya sa movement. Then the blue part is kanang less affected. So the maximum value nga nakuha is 5.561 times 10 to the power of negative 1 amperes, and the minimum is 6.29 times 10 to the power of negative 5. So this is the movement sa shaft. So the next slide shows naman nga ang shaft is ang movement niya is up and down. So mo ni siya ang mode shape 2 na pod. Ang value is 75,5496 hertz. So ang movement ani is up and down. So makita nato sa picture nga ang red part is the disc and some part of the rod nga dool sa disc. So mo na sila mo ang kanang affected area, then ang less affected is ang tip sa rod, which is kanang naka-blue part. So kung once nga mag-up and down, kibali sa center masalo ang vibration kibali kay mo may mupugong ana. So the maximum is 2.768 times 10 to the power of negative 1, while the minimum is 6.150 times 10 to the power of negative 4. So next slide is the simulation. So this is the amplitude 3. Ang value is 75,778 hertz. So kaya na sad is ang movement niya is from left to right. So same ra gyapon scenario sa katong sa amplitude 3, but kanang ang movement kay nakalahi. Still ang most affected area is the center, which is the disc and some part of the rod nga duol sa disc, and still ang less affected is ang tip gyapon sa shaft, which is the color blue nga naa siya 5.404 times 10 to the power of negative 4. Then ang the maximum nga amperes is 2.794 times 10 to the power of negative 1. So this is the amplitude 4 nga naay value nga 371.98 hertz. So ang movement ani is kibali mo siya wave type nga frequency kay kanang so mo siya balod-balod kibali sa shaft. So kani siya is kanang makita nato sa picture nga ang red part is mostly nana sa rod, wala na kibali siya sa disc. So kibali ang disc ani is ga-follow lang gid siya sa wave sa rod nga more siya nagpaanod-anod lang. So kibali ang makadawat sa vibration is the rod nga murag middle sa rod bitaw each both sides from left o right na rod sa shaft. So ang minimum ani nga kuan is still the tip o some part sa disk kay nasay 1.48 times 10 to the power of negative 3. Then the maximum kanang katong naa sa tunga gali sa rad magita man nato sa picture kay naa siya 3.529 times 10 to the power of negative 1. So this is the amplitude 5. Same scenario from the amplitude 4. But same, the movement lang ani is wave siya, wave type frequency, but mer siya sideways ana. So ang still ang most affected area Japan is the middle sa both sides sa rod. Dayon ang less na sad is always the tip of the shaft. And na some part sa disc nga color blue. So ang minimum ano is 8.744 times 10 to the power of negative 4 amperes, and the maximum na sad is 3.531 times 10 to the power of negative 1 amperes.
Hello, I am Ace Nino Arvale, and in our previous slides, Ms. Cherry Estelore had presented us with the modes that we have used during our simulation. So in this slide, we can see our frequency response graph for our simulation. So in the next slide, I will show you the data in tabulated form that we have gathered during our simulation. So in the upper table, we can see the mode list table. So in this table, we can see the frequency number or the number of modes from 1 to 5, the angular velocity of our shaft during our simulation in radians per second, the frequency in hertz, and the time in seconds. So the bottom table is the mass participation. So in this table, we can see the displacement that happened in the shaft during our simulation along the x, y, and z directions. So the sum of the displacement along the x direction from modes 1 to 5 is equals to 0.83546 millimeters. Also, again, the sum of the the sum of the displacement along the y direction during modes 1 to 5 is 0.83545 millimeters. And the sum of the displacement along the z direction is equals to 4.7071 times 10 to the power of negative 7 millimeters. And here we can see the uh, uh, another modal analysis, but this is a result for no loads but with bearing supports as a fixture. So we can see different in the mode list table. We can see different angular velocity, and frequency through modes 1 to 5. The same is also seen in our mass participation table below, with different displacements from x direction, y direction, and z directions. Uh, in this slide, we can see the dimensions that we have used for our model in our simulation. So this is the front view, the side view, and the top view. As you can see, we have 0.0957 meters or 9.7 centimeters of radius that we have used for our disk. We also have 0.05 meters or 5 centimeters of diameter for our shaft, and a diameter of 0.045 or 4.5 centimeters for our bearings. So the total length of our shaft is 1.05 meters. it includes both the shaft and also the bearings. So the thickness of both the bearings and the shaft, the bearings and the disc is 0.025 meters or 2.5 centimeters. As you can see in the side view, we can see the elongation of the disc with a total of 0.007 meters or 0.7 centimeters. So in the next slide, Mr. Kent Atis will present another simulation for no load and no bearings with our shaft.
Uh, I'm the last supporter, so I'm Kanchanati. So I'm going to report the simulation of our model, the uneven disc that has no bearing support, the fixture one. So here's the simulation of the result. With this is the no load and no fixture simulation, just pure frequencies. So I'm going to play it. So you can see that this is expanding. So as we know that our damper is the disc, so mostly the frequency starts to go to the disc and undampen there. So this is the graph. As you can see that the red one in the picture has on the disc there is a red surface. As you can see that. And the other side has the blue surface that is the most unaffected part. As you can see at the right side, there is the coloration scale. As you can see, the highest deformation you can see is the red one scaling, and the lowest is the blue. So this is the second simulation for our 5 natural frequency simulations. As you can see on the result, on the left side of the shaft, there is the red area. That means that the all stress and the vibration coming there. Then this is at the middle part of the affected area of vibration, while the other side has no vibration. This is the video for the third simulation of our frequencies for modal analysis. As you can see in the video that when the shaft and even this turns, at the both ends of the shafts has the most affected area. As you can see it, the red part, while the middle one has less affected. Since in the third frequency, the vibration coming from both ends of the shaft. As you can see, this is the fourth simulation for the no load and no bearing supports. As you can see the movement of the video. So here's the report paper. So here's, as you can see, that the most affected part is the other area, while there is some affection to the other side. On the right side of the shaft, as you can see, it's green level, while the most unaffected is just the middle of the shaft. So this is the last simulation, the opposite one of the fourth one. So as you can see the movement. As you can see, it is an opposite one for the fourth one. The opposite result. As you can see that it is the other side. We have three models or the three datas. So the first one is the graph, which has the highest one is the first simulation, as you can see in the graph, while the lowest is the third simulation, and the middle part is the fifth simulation. So in the table, as you can see, the first simulation the highest amount of radian per second, while also the highest amount of hertz. Do keep in mind that this simulation has no fixture and no loads been applied. So basically the pure frequency of this. So the second is that it has the least amount of time needed. So in as you can see, the third one is the most least radian per second in the hertz, while has the highest amount of time. So in the last one, the resonance, as you can see in the resonance data, the frequency in the x direction, this is the x direction and the y direction and the z direction of which the vibration is being applied. So do keep in mind that our damper is the disk. And also this simulation, the first one and the second one and the third one, we suggest that only we get the data for the third one because the first and third simulation has just same video for them. However, they have different result, which in comes to very high difference. So in this simulation, this is the data for the second simulation with no bearing support as fixture and no load. Basically pure frequency and modal analysis. That's all.